In this video, we're going to look at using gas laws in problem solving. We'll look at Boyle's, Charles, and Gay-Lussac's laws. We'll start out by looking at Boyle's law, and Boyle's law relates pressure and volume. And these two properties are inversely proportional, which means that as one goes up, the other one goes down. So as pressure, for example, increases, that means that volume would decrease. And so let's look at a sample problem. Here we have a sample of nitrogen gas, has a pressure of 1.5 atmospheres and a volume of 570 milliliters. What is the new pressure if the volume changes to 800 milliliters? The temperature and amount of gas is constant. And that last part where it's talking about the temperature and amount of gas being constant is important because those two factors need to be constant when we're dealing with Boyle's law. Okay, so let's go through our problem here. We have an initial pressure of 1.5 atmospheres, so I'm going to label that as P1. And that has a volume of 570 milliliters, and we will call that V1. And then it says, what is the new pressure? Okay, so we're looking for pressure 2. And if the volume changes to 800 milliliters, so that is our volume 2. Okay, so now once we've decided what is what in our problem, let's go ahead and plug those values into Boyle's law. So P1 is 1.5 atmospheres, and volume 1 is 570 milliliters. And that is going to be equal to pressure 2, which is what we're looking for. So we'll leave that just as P2. And then we are, let's see, volume 2 is 800 milliliters. Okay, now some textbooks will rearrange the equation, Boyle's law equation, prior to plugging in the values. I like to plug in the values to the original equation as it's written. I just find it easier. And then once you have the numbers plugged in, you solve for what you're looking for. And so to solve for P2, the first thing we're going to do is divide both sides by 800 milliliters. That will isolate pressure 2 by itself, which is what we are solving for. So I'm just going to divide both sides by 800 milliliters. That crosses that out. Our milliliters cancel. So now we can plug that into our calculator. 1.5 times 570 divided by 800 gives us, and we're rounding to two significant figures, gives us a new pressure of 1.1 atmospheres. Okay, now let's look at Charles' law. In Charles' law, the equation is volume 1 over temperature 1 equals volume 2 over temperature 2. And so Charles' law is looking at volume and temperature, and they are directly proportional, which means that as temperature increases, volume is going to increase. So let's look at the problem we're going to solve. An air bubble has a volume of 50 milliliters at 25 degrees Celsius. If the temperature changes to 35 degrees Celsius, what is the new volume? The pressure and amount of gas did not change. Okay, so for this, we have, let's assign what each of these terms are. So we have volume 1 at 50 milliliters. And temperature 1 is 25 degrees Celsius. I'm just going to put a T1 for right now there. Changes to 35 degrees Celsius. So here's our T2. What is the new volume? So volume 2 is what we are looking for. Okay, now something to keep in mind and remember when you're dealing with gas laws is anytime that there is temperature involved, you have to convert temperature into Kelvin. So when we plug in our temperature values, we'll do that. Let's start by writing out what we have. So our volume 1 is 50 milliliters, and then we're going to divide that by our temperature 1. Well, our temperature 1 is 25 degrees Celsius. So to convert that to Kelvin, we're going to add 273, and so we have 298 Kelvin. So we'll plug that in for T1, 298 Kelvin, and that is going to be equal to V2 And our temperature 2 is, we had 35 degrees Celsius plus 273. And so that is going to bring our temperature to 308 Kelvin. 308 Kelvin. Okay. So plugged all that in. Now we need to solve for volume. So to move 308 to the other side, we're going to multiply both sides by 308 Kelvin. So that cancels that out. So volume 2 is equal. And then we just plug this into our calculator. 308 times 50 divided by 298. Rounding to two significant figures, our new volume is 52 milliliters. So not very much different from our initial volume, but our temperature didn't really change that much either. So that's how to do Charles' law. Our last gas law that we're going to look at in this video is Gay-Lussac's law, and it is comparing pressure and temperature, assuming that volume and amount of gas is constant. And these qualities are also directly proportional, which means that as temperature increases, pressure is going to increase as well. So let's look at a sample problem. Here we go. A sample of gas has a pressure of 4.35 atmospheres at 100 degrees Celsius. What is the pressure when the temperature of the gas falls to 25 degrees Celsius? The volume and amount of gas are constant. Okay, just like before, we're going to assign what each of these things are. So it says at the beginning here, pressure of 4.35 atmospheres. So we're going to say that's pressure 1. At 100 degrees Celsius, that's temperature 1. We'll make sure to convert that to Kelvin before we plug it in. What is the pressure? So this is what we are looking for. Pressure 2, we don't know. When the gas falls to 25 degrees Celsius, that's our T2, and we'll convert that to Kelvin. All right, so let's plug it in. We have 4.35 atmospheres over T1, which is 100 degrees, so 100 plus 273 equals 373 Kelvin. Put that down here. Okay, and that is equal to pressure 2. That's what we're solving for. And T2, 25 plus 273 equals 298. So that'll go down here, 298. Okay, so just like before, we're going to multiply both sides by 298. And that will cancel that out. Our temperature cancels. And so pressure 2 is equal to 298 times 4.35 divided by 373. And in this case, we have three significant figures, and so we're going to say 3.48 atmospheres. Okay, so that is just going through and showing you how to use these different gas laws to solve for problems. So if you're not told which gas law to use, just go through your problem, figure out what qualities or measurements you're taking or that you're given, and then find the gas law that would fit those particular parameters.